In this video, we are going to introduce the concept of plant modeling with Simscape and the physical network approach. Specifically, we will talk about what Simscape is, modeling differences between Simulink and Simscape, building and simulating a model in Simscape, and some general guidelines when it comes to Simscape modeling. This training will be applicable for both the combustion engine and electric teams. Although the basic Simscape concepts are explored with a battery model as an example, they can be extended and applied to many other domains, such as mechanical, hydraulic, or thermal modeling. We would like to acknowledge and thank the Virginia Tech Formula student team for providing us with data about their vehicle, motors, engines, and batteries for us to use in this training. The first question to answer is, what is Simscape? Simscape extends Simulink with libraries for modeling and simulating multi-domain physical systems. Let's switch to MATLAB and see how Simscape and Simulink are related. In MATLAB, we can open the Simulink library browser by typing SL library browser at the MATLAB command prompt. Scroll down to find the Simscape library. It contains models of foundation elements for various physical domains, for example, electrical, hydraulic, mechanical, and more. In addition to this, MathWorks offers a suite of physical modeling products built on top of Simscape for specialized modeling of multi-domain physical systems. For example, Simscape Driveline can be used to model longitudinal dynamics of vehicles, and Simscape Multibody can be used to model 3D systems. With Simscape, you create your model using the physical network method, where deriving the system-level equations is not required. Let's take an example of an RLC circuit here. I will open two models in order to compare the two methods. The model on the left is built using Simulink, and the model on the right uses Simscape. The Simulink model builds the derived equation using integrators and other math operators. It also has signal lines that carry numerical values in a unique direction designated by the arrowhead. The Simscape model, however, uses building blocks like resistor and inductor to build the physical system. There is no necessity to derive the equations for the system. You can also see that the lines don't have arrowheads. These are not the same as Simulink signals. Instead, these are physical connections where the energy flow is bidirectional. Let's go back to the presentation. We just saw the Simscape library and how it extends Simulink. Simscape is built on top of MATLAB and Simulink. There are other specialized add-ons, such as Simscape Multibody and Simscape Driveline, for specific domains that are in turn built on top of Simscape. Simscape also possesses other capabilities that we will talk about later in this training, such as units, data logging, and custom block building. Physical systems can be modeled in Simulink using a signal-based input-output method. This method is flexible but requires deriving and implementing equations at the system level, as shown on the left. With Simscape, you create your model using the physical network method where deriving the system-level equations is not required. This makes your models easier to create, understand, and maintain. In Simscape, the model itself is built using physical blocks and looks more like the diagrams shown at right. We saw the difference between Simulink and Simscape in terms of the connections using an RLC circuit as an example. We have unidirectional signal lines in Simulink and bidirectional physical connections in Simscape. These examples and others discussed in this video series are available for download from the training main page. Finally, note that the approach to creating signal-based Simulink models and network-based Simscape models remains the same no matter the type of system we are trying to model, be it mechanical, thermal, hydraulic, or other. Now let's look at another example. Here we'll take a physical system, model it with Simscape, and simulate it. We are going to take the equivalent circuit of a battery as our example. You can approximate a simple model of a battery as an ideal voltage source connected with a series resistor and an RC parallel bridge. The electrical schematic of the RC circuit is shown here. Let's model this circuit and simulate it to measure the current flowing through it. To start, we'll switch to MATLAB. We can create a new Simulink model through the Simulink Start page, accessible from the MATLAB toolbar. Choose Blank Model. We can open the Simulink library browser through the command line as before, or by clicking the icon on the tool strip. Now we'll drag the blocks we need to the model. Open up the Electrical Elements library found under Simscape Foundation Library. First, we'll grab a resistor. We can add this to the model by left-clicking, holding, and dragging it from the library to our model. This will represent our series resistance. To add a second resistor, we can repeat the same procedure, or we can simply right-click on the existing resistor and drag it to create a copy. We will add a capacitor also from the Electrical Elements library. Next, we need a voltage source. This can be found in the Electrical Sources library. We will choose DC voltage source, left-click, and drag to add it to our model. Finally, we also need an electrical reference. This can be found under the Electrical Elements library. This represents the ground terminal for the circuit. Most portions of physical networks representing a physical domain will include a domain-specific reference block. This establishes a reference level for physical quantities, such as voltage or velocity. For example, a DC motor, which contains electrical and mechanical domains, must include at least one electrical ground and one mechanical reference block. In this case, we only need one electrical ground. Now we need to create the connections. First, let's maximize this so that we can see all of our components. You can zoom in or out using the scroll wheel, or by pressing spacebar, you can cause the components to fill your screen. To create a connection, simply click on one port and drag the signal line to the next port. You can also control-click on a block and click the next block to automatically create a connection. Let's also connect the positive end of the DC voltage source to the series resistor. Now we need to connect this resistor to the RC parallel bridge. The same procedure applies, and a branch will automatically be created. If you'd like to make a branch from an existing signal, you can control-click on that signal and a new branch will appear. Let's connect this to the negative end of our voltage source. We'll also need to connect the electrical reference block to define the ground. We will choose the negative terminal of the DC voltage block, although the dynamics would be the same regardless of which point we choose. In a mechanical system, however, the position of the reference is physically important and represents anything rigidly attached to the frame. Note that as you connect these blocks together, the physical connections will be colored blue. This represents a connection in the electrical domain. To view a legend of all domain colors, select Display, Simscape, Legend. This shows all of the colors for the available domains in Simscape. In the same menu, you can also disable the coloring of physical connections by unchecking the Domain Styles option. I won't do this now, though. Many Simscape blocks can be configured by double-clicking them and editing their dialogs. In this way, you can change the parameters for each component in a physical network. Double-click the DC voltage source and change its constant voltage to 4.2 volts. Note here that this value has associated units. Simscape supports units. Based on different quantities like voltage and current in the electrical domain and velocity and force in the mechanical domain, many units are available for these quantities. Let's switch back to MATLAB for a bit to see this. Execute the command pm_getunits to get a list of all the units that Simscape supports. Let's go back to the model now and finish setting our parameters. We'll double-click the resistor to set its parameters in the same way. Let's give it a value of 0.01 ohm. We will set this resistor to a resistance of 0.005 ohm. Let's set the capacitor block capacitance to 5,000 farad. Note that the capacitor and resistor blocks had another tab called Variables. This can be used to set initial conditions for variables, such as the initial capacitor voltage. This is covered in the Simscape Fundamentals video. We can also make block values appear directly on the model by setting appropriate block annotations. For example, let's choose this resistor. Right-click on it and choose Properties. Open the Block Annotation tab. There are several properties we can show on this. Let's scroll all the way down and choose the resistance R and its units. We can customize the display in the window at right. After clicking OK, now we can see the value without having to double-click on the block. We can also change the value, and the changes will register in the model. Now we'd like to observe the current flowing through the circuit. For this, we are going to use a Simulink Scope. Current and other physical quantities in Simscape models can be measured using sensors and can be passed through the model using Simulink signals. First, let's add a sensor block to the model. The current sensor can be found in the electrical sensors library. Let's make some room here in our window. We can zoom out with the scroll wheel, or we can click the wheel and drag to pan. Drag this to the model. Just like in a physical signal, we have to put the current sensor in series. Note that the current path is shown in blue, indicating that it is a physical electrical signal, and that the output of the sensor has a triangular connection. This indicates that it is a physical signal as well and carries units. A physical signal cannot be connected directly to Simulink blocks since Simulink signals are numerical. Thus, we need a physical signal to Simulink converter block. A convenient way to add blocks to a model, if you know their name, is to click in the Simulink editor and begin typing the name of the block. Here we have added the physical signal to Simulink converter block. There is, of course, a Simulink to physical signal converter block. Both of these can be found in the Simscape utilities library. Let's connect the sensed signal to the converter block. This acts as an interface between the physical domain and Simulink. Since Simscape supports units, we can specify any units or conversions before we convert to the Simulink domain. This is done by double-clicking on the block. The default unit here is 1. This means that the unit is not specified. Let's specify ampere. Now we can visualize this signal using the Simulink Scope, which is located in the Simulink Sinks library. One final step remains before we simulate the model. All Simscape models require a solver configuration block. This can be found in the Simscape Utilities library. Drag the block to the model and connect it anywhere in the circuit. It does not matter where. This is used to define solver settings for each physical network and tells Simulink what options to use to solve this particular physical network. Note that a Simscape model can have more than one network, hence more than one solver configuration block. In our case, we only have one network. Next, when simulating a Simscape model, certain Simulink solvers are recommended. Let's open up the solver parameters in the configuration parameters window by clicking the gear icon or hitting Ctrl-E on your keyboard. The recommended solvers for Simscape models are ODE 15S, ODE 23T, and for fixed step simulations, ODE 14X. We will use ODE 15S here. Models created with Simscape blocks are solved differently from models created using Simulink blocks, even if the underlying equations are identical. This is one of the reasons the recommended solvers are different for the two approaches. More information about this can be found in the documentation. Set the stop time to 100 seconds. This specifies the amount of simulation time for which the model will run. Click OK to return to the Simulink editor. You can also change the stop time directly in the toolbar here. Simulate the model by hitting the Run button and double-click the scope to open it. Hit the Auto Scale button to bring the waveform into view if it is not already. Congratulations! You have just created and simulated your first physical system in Simscape. Simscape models can contain many different physical domains. Let us take an example. Here I have blocks with varying domains. However, you can only connect physical ports if the blocks are of the same physical domain. For example, on the left we have two blocks from the electrical domain. These can be connected. Simscape will not permit you to directly connect physical ports that are of different domains. Here we have a hydraulic reference and a mechanical translational damper. These cannot be connected. Note that you can create multi-domain models in Simscape. This will be discussed in the Simscape Fundamentals video. Let's go back to the presentation and recap what we've just done. We built the equivalent circuit of a battery by dragging and dropping resistors, a capacitor, and a reference block from the electrical elements library. We also added a DC voltage source from the electrical sources library and a solver configuration block from the utilities library. We then set parameters for the blocks by double-clicking and editing the parameters for each one of them. At this point, the model of our physical system was built. To interface between Simulink and Simscape, we can use Simulink to physical signal and physical signal to Simulink converters. Since we are measuring current, we are using a current sensor and placing it in series with the circuit. There are also other sensors available based on what quantities we want to measure. We were then ready to simulate the model. We talked about solvers and how Simscape models are simulated differently when compared to Simulink models. The recommended solvers for Simscape models are ODE 15S, ODE 23T, and ODE 14X for fixed step simulations or local solvers. We saw that we can change the simulation length directly in the Simulink editor and used a Simulink Scope block to visualize our signal. We also talked about essential Simscape blocks. Every physical network in a Simscape model should have a solver configuration block. These are used to set the solver parameters per network. Note that a Simscape model may have more than one physical network and hence more than one solver configuration block. Most Simscape models also have domain-specific reference blocks to provide a reference level for the various physical quantities in the system. Finally, we talked about multiple domains in Simscape and how we can interconnect only blocks from the same domain. A Simscape model could be multi-domain, and we will talk about this in the next video on Simscape fundamentals. In summary, we talked about what Simscape is, the differences between Simulink and Simscape, building and simulating a Simscape model, and guidelines for Simscape modeling. This concludes the video.